Hi guys, so sorry I can't be there. Wish I could be, but my 3.5-year-old called me into her room at 3 a.m. and sure enough, she had thrown up. So that is why I'm not there. So I'm going to go through these Dalton and gastrostochiometry notes with you. So it might be a good idea for you to do like a split screen or something like that so you can listen and follow along. So we're going to learn one new law, and that's Dalton's law of partial pressure. It's a very straightforward law. It's that the total pressure inside a container is the sum of each individual gas pressure inside of it. So meaning, like here, we have a bunch of different ones, right? We have helium and nitrogen and oxygen. So the total pressure in there is the sum of all those. So the 1 atm plus 1 atm plus 1 atm equals the total pressure inside of the container with all of them. So the answer would be 3 atm. So with this law, you just need to make sure that the pressure units are in the same. Pressure units are the same for each of them. So it could all be mmHg, it could all be atm, it could all be kPa. But they all obviously need to be in the same pressure unit. When we talk about the pressure of different gases, the pressure of the gas is affected by the number of particles, not the identity. Meaning it doesn't matter that it's helium, it doesn't matter that it's oxygen. What matters is the number of particles. So, for example, if I'm looking down, which one do I want to do? Let's look at this situation. So, looking at this, we have 1 mole of nitrogen, 0.5 moles of oxygen, and 0.25 moles of argon. But we know that the total pressure in there is 8.4 atm. Well, I could easily figure out the individual pressures of the nitrogen, oxygen, and argon because, like I said, it's all about the number of particles. So, looking at this, the percentage that is the nitrogen, right? 1 mole out of 1.75 moles is due to the nitrogen. So that's like 57%. 0.5 if we're doing it in decimal form. Times the whole pressure is 8.4. So nitrogen's, the pressure due to nitrogen is 4.8 atm. So then I could figure out the same thing for oxygen. I'll do, I guess, oxygen over here. 5 moles of it, 0.5 moles out of the total moles, 1.75. So that is 0.285 times, right, the 8.4. Means pressure due to the oxygen is 2.4. So then I could figure out the argon, right, 2 different ways. I could either do 8.4, right, the total pressure, minus our nitrogen and oxygen pressures that we already know, because the remaining is due to the argon. So 4.8 minus 2.4. .2 atm for the argon, right? And then the other way that we could do it is doing the parts of a whole, the percentage again, taking 0.25 over 1.75, figuring out what percentage of all the molecules are due to argon, and then multiplying it by that 8.4. So just parts of a whole, because the pressure inside of the container is due to, like I said, the number of particles. It does not matter the nature of the particles, not the identity. It doesn't matter about that. It's all about the number of particles. Okay, so here we have a practice problem. It says you have a 5 gram sample of helium gas is added to a 5 gram sample of neon, a container with 2.5 liters at 27 degrees. So remember, right when you see something in Celsius, go ahead and add 273 to get it to Kelvin. So that's going to be 300 K. All right, calculate the partial pressure of each gas and the total pressure. So do you have any clue, any law, what we should be using here at first? Letting you think. Okay, hopefully you maybe thought we should use Pivnert. PV equals nRT, because we have our grams, right, of each one. So we can convert those to moles and then use Pivnert and solve for pressure. So we'd obviously be needing to use a Pivnert with helium and a Pivnert for neon. PV equals nRT. So for helium, we don't know the pressure. We know that we have 2.5 liters. Equals. Okay, so let's go ahead and convert our 5 grams of helium to moles. Molar mass of helium is 4. So 5 divided by 4. So that's going to go in for our N, 1.25. R, we know it's always 0.0821, and our temperature we said is 300. Okay, then we'll solve. .3, but we need 2 6 12 ATM. Now we'll do our neon. So 5 grams of neon. Neon. Mole of neon. Gets 20. Yes. 183. So now we're going to set up our Pivnert. So we don't know pressure, no volume is 2.5, N is 0.247, R is 0.0821, and then our T is 300. So we have this answer for helium, this for neon. So now our total, right, it's just going to be our 12 plus 2.4. So we get 14.4. Sig figs, we care about past the decimal. Remember, you go with least past the decimal when you're adding or subtracting. So we should only have none past the decimal. So 14 ATM would be the total. Hopefully that one made sense. Alright, for here it says you have 27.4 liters of oxygen gas at 25 degrees Celsius. Let's go ahead, 298K on that, and 1.3 ATM. Then you have 8.5 liters of helium gas at 25, so that's 298K in, right? 2 ATM were pumped into a tank with a volume of 5.81 liters at 25 degrees. So temperature is staying constant the whole time. Calculate the new partial pressure of oxygen. I'm giving you a minute to think through what you're given here. So I think there's 2 different ways that you could set this up. For me, when I read this, the thing that comes to my mind is to go ahead and use your like initial and final volume and pressure. So volume and pressure would be boils, right? So your initial pressure for your oxygen was 1.3, right? Because PV equals PV. Pressure times volume. We're trying to figure out pressure with the new volume of 5.81. I think you could have also used Pivnert. I think it would have taken just a little bit more. You could have solved for moles initially and then put it into Pivnert again with the new volume, if that makes sense. Six point, what, 366? 13. ATM. Calculate the new partial pressure of helium. So I do the same thing. So initial pressure of the helium was 2 times the volume of that helium was 8.5, and the new volume was 5.81. Right, now calculate the new total pressure. So we just add now. 6.13 plus 2.93. Okay, so now we're going to move on to gas stoichiometry. So with gas stoichiometry, it says writing and balancing equations. Balanced equations relate moles and grams, right? We've learned that we can use those mole ratios, like the numbers up front, to tell you how many moles you have of it in terms of like the coefficients in your balanced equation. But they can also be used for volumes, meaning we can get a volume ratio of the gases. So if I had, a gas, O2 gas, and I'm making H2O gas, let me balance it. Right. Okay, so that means for every 2 liters, right, of H2, I could say there's 1 liter of O2, or for every 2 liters of H2O makes, or it doesn't make, it comes from 1 liter of O2.